There is a substance born from the explosions of ancient stars, traveling across billions of years to lie dormant within the Earth, waiting for the day it would shake the course of human history in ways no one could foresee. It is not food for survival, yet people are willing to trade everything to possess it, even sacrifice their entire lives in pursuit of it. That substance is gold. You can see it shimmering on the jewelry of the elite or standing proudly in finely crafted works of art. It quietly drives the flow of technology inside supercomputers and space satellites. And more than that, thousands of years ago, it became one of humanity's earliest forms of currency, used for exchange, storing value, and shaping the economies of ancient civilizations. But have you ever wondered, to achieve such brilliance, what intense ordeals it had to endure in blazing furnaces and through extraordinarily intricate refining processes? Stay tuned to the Terran Works channel as we uncover the true power and origin journey of this eternal light. Gold's presence in the flow of history goes far beyond its shimmering appearance. It quickly became a symbol of divinity and immortality in the minds of ancient people. From the powerful funerary masks of Egyptian pharaohs to the exquisitely handcrafted jewelry of modern artisans, gold is the only metal that defies time by never oxidizing, preserving the belief in an eternal value. This rare quality and remarkable durability have turned gold into the most steadfast anchor of the global economy. For thousands of years, it has served as the standard measure of prosperity and a safe haven that nations turn to in order to protect their financial lifeblood against the turbulence of inflation. Yet in the digital age, gold has embarked on a new, quiet but powerful journey within the world of high technology. Thanks to its near-perfect electrical conductivity and chemical stability, gold has become the soul of microscopic circuits, ensuring that every signal in your smartphone flows seamlessly. From a treasure in ancient tombs to an essential material on space stations, gold continues to prove that, in any form, it remains the silent force guiding the advancement of civilization. For this reason, gold is not merely a metal, but a symbol that runs through every civilization, from ancient to modern. The California Gold Rush began in 1848 when James W. Marshall accidentally discovered the first flakes of gold at Sutter's Mill in California. At first, the news was kept secret, but it quickly spread across the United States and even around the world. Hundreds of thousands of people, known as the 49ers, abandoned their jobs, families, and stable lives to plunge into a risky adventure, hoping to find gold and transform their lives overnight. Rivers, hillsides, and valleys soon turned into bustling mining sites, where people worked day and night under harsh conditions. However, reality fell far short of the dream. Only a small number struck it rich, while most faced failure, disease, and poverty. Even so, the gold rush significantly boosted the economy, attracted waves of settlers, expanded territory, and transformed California from a remote frontier into a major center of development in the United States. Those who came in search of gold often carried hope but left with hard-earned lessons. It is precisely this contrast that created the enduring legend of gold rushes throughout history. From these explosive gold rushes, people quickly realized that easily accessible gold would not last forever. As luck ran out, the search for gold had to shift toward more scientific and technologically advanced methods. From that point on, gold's journey entered a modern era of extraction and refinement, where every particle is separated through precise techniques. The first stage is exploration and preparation, a foundational step to determine the existence and scale of a gold deposit. Geologists employ various methods such as topographic surveys, soil and rock sample analysis, magnetic and seismic measurements to identify geological structures that may contain gold. They then carry out exploratory drilling to extract core samples from deep underground, which are analyzed for gold content and associated minerals. The collected data is processed using geological modeling to estimate reserves and assess the economic feasibility of mining. If the deposit shows potential, preparation steps are initiated, including mine design, extraction planning, and the construction of infrastructure such as transportation routes, water supply systems, and electricity networks. In addition, environmental and legal factors are carefully evaluated to ensure regulatory compliance and minimize negative impacts. This stage requires significant investment in time, technology, and cost, but it plays a decisive role in ensuring the efficiency and safety of the entire gold mining process that follows. After the exploration and preparation phases are completed, the ore extraction stage begins, aiming to bring gold-bearing material to the surface. Depending on the location and characteristics of the deposit, mining can be carried out using either open-pit or underground methods. In open-pit mining, the overlying layers of soil and rock are stripped away using excavators and large haul trucks to access the ore body. Meanwhile, underground mining requires the construction of deep tunnels, where drilling and blasting equipment is used to break apart gold-bearing rock. Once extracted, the ore is transported to processing facilities. During this stage, strict safety control is essential due to risks such as tunnel collapses, toxic dust, and machinery-related accidents. At the same time, environmental protection measures such as dust suppression, wastewater treatment, and land rehabilitation are implemented to minimize negative impacts. The efficiency of the extraction stage depends heavily on technology, engineering, and operational management, as it directly affects production costs and the amount of gold that can be recovered in subsequent steps. This is also the point at which humans confront nature in its most raw and unforgiving state. Every ton of ore brought to the surface is not only the result of machinery, but of an entire complex operational system, behind which risks are always present. Once the ore is transported to the processing area, the next stage is no longer about massive raw rocks, but a carefully controlled size reduction process, down to fine detail. Initially, the ore is fed into a jaw crusher, where strong compressive forces break large rocks into smaller fragments. The material then passes through cone crushers or roll crushers for further size reduction before entering the fine grinding stage. At this point, ball mills operate continuously, using steel balls that collide and create friction to grind the ore into a fine powder. The core objective of this stage is to liberate as many gold particles as possible from the surrounding mineral matrix, allowing them to be exposed and ready for extraction. However, grinding cannot be done arbitrarily. If the particle size is too large, the gold will not be fully liberated. But if it is too fine, energy costs increase significantly and subsequent separation processes become more difficult. Therefore, classification systems such as vibrating screens and hydrocyclones are integrated to precisely control particle size. Properly sized particles move forward, while oversized material is recirculated for further grinding. This step lays a crucial foundation, ultimately determining the efficiency of gold recovery throughout the entire downstream process. Once the ore has been ground to the appropriate size, the gold is still not in a free state and must be separated using chemical methods. The most common technique is cyanide leaching, in which the powdered ore is mixed with water and chemicals to form a slurry. In this environment, gold reacts and dissolves, forming compounds that can be separated from the remaining residue. Agitated tank systems or heap leaching setups are designed to optimize contact time and recovery efficiency. This stage is critical to economic performance, as even slight deviations in chemical concentration, pH levels, or processing time can significantly reduce the amount of gold recovered. At the same time, due to the toxic nature of some of the chemicals involved, strict environmental and safety control systems are implemented to prevent leaks and protect the surrounding ecosystem. After gold has been dissolved in the solution, the next step is to recover this precious metal in solid form through precipitation. Depending on the technology used, gold can be adsorbed onto activated carbon or precipitated using metals such as zinc. When activated carbon is applied, gold particles in the solution adhere to the surface of the carbon, which is then separated and further processed to recover the gold. In the case of zinc, a chemical reaction causes the gold to settle as metallic sludge. This gold-rich material is then filtered, washed, and dried before being sent to the smelting stage. Inside the furnace, high temperatures melt the mixture, while fluxes are added to help separate impurities from the metal. Lighter impurities rise to the surface as slag and are removed, while the heavier metal settles at the bottom of the furnace. The result is a crude gold alloy, commonly known as doré, which contains gold, along with small amounts of other metals. This marks a crucial transition from a dissolved state to a tangible metal form, laying the foundation for the next refining stage to achieve higher purity. From the doré alloy, gold's journey enters its final stage, but also the one that demands the highest level of precision: refining and assaying. At this step, the objective is to remove all remaining impurities to achieve near absolute purity. In parallel, chemical processes continue to treat any residual contaminants, ensuring that even the smallest errors are eliminated. Once the required standard is reached, the gold is melted and cast into bars or standardized product forms. However, the process does not end there. Each gold bar must undergo strict weighing using high-precision equipment, where even the smallest deviation can affect its market value. The verified weight, combined with purity, determines the true value of the gold. The samples are then sent to laboratories for assaying, where advanced analytical technologies precisely determine the metal content and ensure compliance with international standards. Only after passing all these stages does gold truly complete its journey, from a lifeless rock beneath the ground to a high-value asset ready to enter the global economic system. But gold's value is not solely defined by its form or external shine. It lies in the absolute precision, verified through every measurement and every strict standard. Yet there is one thing few people realize. The journey of gold we have just followed may not be its final destination. If gold was born from the explosions of ancient stars, then humanity's largest sources of gold may not lie beneath the Earth at all, but out in space. Scientists have discovered many asteroids containing massive amounts of metals, including gold. One notable example is the asteroid 16 Psyche, estimated to be worth thousands of trillions of dollars, a figure large enough to potentially reshape the entire global economy. The idea of mining gold in space is no longer science fiction. Many organizations have already begun researching ways to reach these extraterrestrial gold mines, where instead of digging hundreds of meters underground, humans would have to travel millions of kilometers through space. But it raises a deeper question. If one day gold becomes nearly limitless, would it still hold the same value it does today? This is the greatest paradox of gold. Its value is not only based on rarity, but also on belief. The belief that it is scarce and worth pursuing. If that belief changes, the entire meaning of gold in human history could change as well. From the depths of the Earth to the vastness of space, gold has never been just a metal. It is a symbol of humanity's boundless ambition. So we have now gone through the entire journey of gold, from the gold rushes that once turned the world upside down, to the highly precise extraction and manufacturing processes down to the smallest detail. What is fascinating is that gold's value is not only rooted in its rarity or purity, but also in the entire system of humans, technology, and time that has shaped it. Every gram of gold you see today is in reality the result of millions of years of formation and hundreds of complex processing stages. And perhaps, once we understand that, gold is no longer simply something that shines on the surface, but becomes one of the most meaningful materials in human history. Formed from stellar explosions billions of years ago, uranium is one of the oldest elements on Earth. Yet it was not until the late 19th century that humanity truly recognized its significance. When the scientist Henri Becquerel discovered that uranium could spontaneously emit radiation without any external energy source. This breakthrough opened the door to an entirely new field, nuclear physics, laying the foundation for revolutionary advances in the 20th century. In nature, uranium does not exist in its pure form. Instead, it lies hidden within rocks and minerals, such as uraninite and pitchblende, ores shaped over millions of years through geological transformations. The structure of uranium possesses extraordinarily complex physical properties. Within it lies the potential to release immense streams of energy through nuclear reactions, a latent power that has remained dormant deep within atomic structures since the earliest moments of the universe. It is precisely this inherent power that makes uranium such a unique material. Its entire mass conceals an extraordinary capacity for impact, strong enough to bring about transformative, world-changing shifts for humanity. When used in energy systems, uranium is not merely a fuel. It represents one of the most stable and powerful energy sources ever harnessed by humanity. Unlike wind or solar power, which depend on natural conditions, nuclear energy derived from uranium can operate continuously 24/7, providing a stable flow of electricity to cities, industrial zones, and entire modern infrastructures. This is especially crucial in a world that is increasingly dependent on electricity, from data and transportation to manufacturing. From a broader perspective, uranium does not only generate power, it helps maintain the stability of the entire energy system, acting as a silent backbone of the modern world. Besides its role in energy production, uranium is also closely tied to one of the most sensitive and controversial fields in modern history: nuclear weapons. Uranium is not only fuel for civilian reactors, but also a core material in the development of nuclear armaments. Unlike electricity generation, where uranium is carefully controlled to produce stable energy, in a military context, the same element becomes the foundation for technologies with destructive power far beyond any conventional weapon. It is precisely the ability to release enormous amounts of energy through nuclear reactions that has made uranium a central factor in the weapons programs of many countries. From events such as the atomic bombings of Hiroshima and Nagasaki to the arms race during the Cold War, uranium has played a crucial role in shaping the global balance of power. Its presence carries not only technological significance, but also serves as a tool of deterrence, where power does not necessarily have to be used, but always exists as a factor influencing political and military decisions. For this reason, uranium today is not just a natural resource, but a strategic issue. The control, monitoring, and restriction of its proliferation have become an essential part of global efforts to maintain stability and security worldwide. Because of this exceptional role, uranium is not only regarded as an energy resource, but also as a strategic mineral, where every ton of ore carries economic value, technological significance, and even geopolitical implications. But before uranium can become fuel or be used for any application, it must first be discovered deep underground, hidden among millions of tons of rock that are nearly indistinguishable to the naked eye. This process begins with geological surveying, where scientists use radiometric measurement equipment to detect extremely subtle traces of uranium in nature. From the air, from the ground, and even through exploratory drilling hundreds of meters deep, data is continuously collected to determine whether economically viable ore bodies exist beneath the surface. Potential areas are then analyzed in greater detail, from geological structure and depth to the concentration levels of uranium within the rock. Not every discovery becomes a mine. Only those that meet sufficient conditions in terms of reserves, extractability, and cost are selected. At this stage, uranium is still only an invisible signal deep within the Earth. Yet it is from these signals that the entire chain of extraction and production eventually begins to take shape. When a region is confirmed to contain sufficient uranium reserves, the extraction process begins, and this is also the moment when uranium transitions from an underground signal into a tangible resource. However, there's no single method applied to all deposits. The mining approach depends entirely on depth, geological structure, and environmental conditions of each site. In areas where the ore is close to the surface, the overlying soil and rock are removed to expose the ore body. But in many cases, uranium lies hundreds of meters underground, forcing engineers to dig long tunnels through ancient rock layers to reach it. This is a harsh environment, where groundwater pressure, temperature, and radiation are constant factors that must be strictly controlled. In some modern mines, instead of deep excavation, in situ leaching is used. A solution is injected underground to dissolve the uranium, which is then pumped back to the surface. This approach helps minimize disruption to the landscape, but requires extremely precise control to avoid environmental impact. Regardless of the method, the ultimate goal remains the same: to extract uranium ore from the earth, while ensuring human safety and maintaining stable operations in an environment that is always inherently risky. After being brought up from underground, uranium ore still has little practical value. At this stage, it is simply raw rock, with uranium tightly locked within the mineral structure. To release the energy hidden inside, the next step begins: crushing and processing the ore. Large rocks are fed into industrial crushers, where they are broken down into smaller fragments and then further ground through multiple stages. Each stage is designed to reduce the material to an optimal size, from several centimeters down to fine sand-like particles. This process is not merely about making the material smaller. It is about increasing the surface area, allowing uranium to be extracted more efficiently in subsequent processing steps. After crushing, the ore is mixed with water to form a slurry. In this state, the material can be pumped, transported, and processed within a closed system, reducing losses and allowing tighter control of environmental factors. From this point on, uranium ore is no longer solid rock. It has become a controllable material, ready for the most important stage: separating uranium from the surrounding waste minerals. When the ore has been turned into a slurry, uranium enters a chemical surgical operation to separate itself from useless rock. Instead of physical crushing, acidic or alkaline solutions are used with precise targeting to dissolve the uranium, freeing it from the mineral structure that has trapped it for millions of years. Invisible to the naked eye, uranium at this stage is ready to reveal itself through the purification process. By carefully controlling temperature and chemical concentration, uranium begins to precipitate, settling at the bottom of the tank as fine particles. After filtration and drying, it condenses into a distinctive yellow-brown powder known as yellow cake. However, the journey does not end there. To reach a higher level of control, yellow cake is further processed through a series of reactions to become uranium hexafluoride, UFCs. This is a decisive turning point. At temperatures just above 50 degrees Celsius, uranium sheds its solid form and becomes a volatile gas. This unique physical property opens the gateway into the atomic world, where humans can manipulate the extremely subtle differences between isotopes, something impossible with raw materials. From massive rock formations at the beginning, uranium has been continuously refined and transformed to reach its most sophisticated state. Precision is no longer measured in millimeters, but in nearly invisible differences between atomic particles, ready for a new chapter of extraordinary power. Although uranium has been converted into a gaseous state, it is still not ready for use. In nature, the fissile isotope uranium-235 makes up less than 1% of the total mass, far too little for efficient energy production. Therefore, uranium must undergo an enrichment process, where the proportion of uranium-235 is increased using centrifuge systems spinning at extremely high speeds, reaching tens of thousands of revolutions per minute. Inside these machines, uranium in gaseous form is subjected to powerful centrifugal forces, allowing the very small mass differences between isotopes to become significant. The heavier fraction is pushed outward, while the lighter uranium-235 concentrates closer to the axis of rotation. After enrichment, uranium is no longer kept in gaseous form, but is converted back into a more stable solid state. At this stage, the material is processed into uranium dioxide, a compound capable of withstanding high temperatures and suitable for the extreme conditions inside a reactor. From a fine powder, uranium dioxide is pressed under high pressure into small fuel pellets only a few millimeters in size, yet containing extremely high energy density. These pellets are then sintered at high temperatures to form a ceramic-like durable structure. The pellets are loaded into special metal tubes, typically made of zirconium, which are then sealed to form fuel rods. Finally, these rods are assembled into complete fuel bundles, marking the transition from raw material into a precisely engineered system, ready to release energy at the atomic level. Before uranium can become fuel for nuclear reactors, it must travel a long journey across multiple countries, oceans, and highly stringent security control systems. This is a stage rarely mentioned, yet it plays a crucial role in the entire global nuclear supply chain. Along every segment of the route, uranium is tightly monitored. Transportation corridors are secured, security forces accompany shipments, and the entire journey is continuously tracked to prevent any risks, from accidents to security threats. Even a minor mistake during transport could lead to serious consequences, not only environmentally, but also politically. What is remarkable is that despite carrying one of the most sensitive materials on Earth, most of these shipments take place in silence, almost invisible to the outside world. And it is precisely this silence that reflects a clear reality. Behind every kilowatt of nuclear electricity lies a complex operational network, where uranium is not only extracted or processed, but must also be protected at every kilometer of its journey.